The next topic is sampling theorem. So what is sampling? Sampling is the process by which samples are taken from a continuous signal, or by sampling process an analog signal is converted to digital signal or discrete signal. So if you want to get the original signal back, suppose we have an analog message signal, it is converted to discrete by using sampling process. If you want to convert to original message signal back at the receiver, or you want to reconstruct your signal, it is necessary to take sufficient number of samples, then only the reconstruction of original signal is possible from the samples. So normally, how many number of samples should be taken when we convert an analog signal to digital signal or a continuous time message signal? When we are discretizing it, how many number of samples we need to take? It is depending on the maximum frequency of your analog signal or analog message signal. So always, how many number of samples should be taken for discretizing? It is depending on the maximum number of maximum frequency present in the message signal. According to that, if we have taken the sample, only we will be able to reconstruct it. So we will see in detail how it is. Here I have So here we have shown here the message signal MT. See here FM is 2 Hz. That means in 1 second time there are 2 cycles. So message frequency is taken as 2 Hz. See, message frequency means message signal may contain different frequency. In that case, take the highest frequency of that signal. So here only one frequency is shown, and so I have taken it as 2 Hz. Just for an example I am explaining this. Now, for making you to understand clearly about sampling. So, Fs. See here, carrier pulse I have taken as 8 Hz. That is 8 cycles per second. So, here in 1 second time there are 8 pulses. Now, when you sample it, or modulating it, you just multiply carrier and message signal. So, the corresponding to these two, that corresponding amplitude will come over here. Corresponding to these two, this corresponding amplitude of sinusoidal will come here. Here, this it will come here. This two it will come here. Now, if you want to reconstruct the signal, so now I sampled and I can transmit it. Now, suppose at the receiver I have to reconstruct the signal. Now, you need to reconstruct the signal means it is easy. I can just draw the envelope of the signal. You can just see if I am just drawing the envelope of the signal. See, I can get the same signal in 2 cycles per second. Same, maybe amplitude variation will be there because of the noise. But see, I can reconstruct exactly same signal. So how many number of samples here I have taken for this message signal? I have taken 1, 2, 3, 4, 5, 6, 7, 8. 8 samples I have considered. So for corresponding to this message signal, now I represented with 8 samples. I represented with 8 samples. Now, so now you just check our FM is how much? FM was only 2 and Fs sampling frequency, how many number of samples? 8. Of course, here Fs is greater than Fm. But how much time it is greater? Around 4 times. Fm is only 2. This is Fs is around 4. So I can write here, I have taken here the Fs. That means the 8. It is 4 times Fm. That is 8. Isn't it? So just for an example I am telling. So Fs is 4 times Fm I am considering. Now again consider the same example over here. But here I have reduced Fs samples as 4 Hz. So in the previous slide, I have shown 8 hertz, 8 number of samples. Current, I have shown only 4 hertz. So now, for the message signal, correspond same message signal being drawn with 2 hertz. How many number of samples I have taken? Only 4 samples. Only 4 samples I have considered over here. So now if you look here, corresponding to this, the corresponding amplitude will come here. Corresponding to this sample, corresponding amplitude of message will come here. This sample, the corresponding amplitude of message. So I am drawn with the number of, I just represented my message signal, continuous time message signal completely in terms of samples. So now see, can I able to at the receiver, can I able to reconstruct the signal if I receive only the samples? Yes. Just again try to draw the envelope and see. I can just draw the envelope. I can approximately get the same shape. You can just see here. Envelope means outside I am just drawing or I am just filtering it. So again I can just get the same type of signal. See, again I am able to reconstruct a signal. How many number of samples? 4 samples. So here I have taken my FM as 4 hertz and my FS also as, FM as 2 hertz. FM I have taken as 2 hertz and FS as 4 hertz. So now FS is greater than FM. How much time? Here I have considered FS is equal to 2 times FM, isn't it? Because Fs is 4, so it is 2 into 2, 4. So here I have considered Fs is 2 times Fm. In the previous slide I have considered Fs is 4 times Fm. Here you have seen, you will be able to reconstruct. Here also you have seen, you will be able to reconstruct. Now again see the another case. Here I am taking Fs is 2 samples per second. Only 2 samples I am taking. So now I have the message signal. I have only 2 samples here. Now try to reconstruct. So and the transmitted signal will be something like this. Try to reconstruct the signal. So if I am able to reconstruct the signal, I don't have anything down, only 2 samples. So I am maybe just able to reconstruct something like this. I cannot get this shape. I cannot get this frequency of message signal. That means here I have considered my FM was 2 hertz and my Fs is how much? Only 2. Again Fs is also 2 hertz. So here I have taken Fm equal to Fs. Can you able to reconstruct? No, you cannot reconstruct. So if you want to reconstruct your signal, you have to choose the number of sample or sampling frequency at least 2 FM or greater than 2 FM. This is what is called Nyquist theorem. So the Nyquist theorem or a sampling theorem states that you have a band emitted signal with no spectral component above FM. So that means sampling theorem states that the maximum frequency of a message signal is FM. This is the maximum frequency. Now if you want to reconstruct the signal properly, your sampling rate Fs should be greater than or equal to 2 times FM. If it is less than 2 FM, you have found this case as you cannot reconstruct it. So Fs should be greater than or equal to 2 times FM. Then only you will be able to reconstruct the signal. So this is called a sampling theorem. This is called a sampling theorem. Or even you can write Ts. You know what is Ts? Ts should be equal to 1 over Fs. So I am just replacing this with Ts. So how my equation will be? The same equation if I am writing 1 over Ts, that is Fs, should be greater than or equal to 2 times Fm, or cross multiply, you can get it as 1 by 2 Fm should be greater than or equal to Ts, or Ts should be less than, the same expression only this and this, Ts should be less than or equal to 1 by 2 Fm. It's derived from here. I hope that this is clear for you now. Fs should be greater than or equal to 2 times Fm. And Fs is equal to 2 Fm. That equality condition, that is the maximum border allowed. So this is called a Nyquist rate. This is called a Nyquist rate. Now consider the sampling theorem again in the frequency domain case. So we will take our first condition. What our first condition? Our first condition, we have taken Fm 2 Hz and Fs 8 Hz. So our Fs is 8 Hz. So now here in frequency domain, each sample I am representing by some symbol like this. So for example, my Fm is 2 Hz. So this should be represented by 2 Hz. This should be Fm and this should be minus Fm. So 2, 2, our first sample is drawn. Now second sample will come as Fs. What is our Fs in the first case? Fs at the first case was 8. We are taken 8 samples per second. So Fs was 8 Hz. So after 0, the next sample should come at next sample should taken at 8 Hz and next should taken as 16 Hz. So now at Fs, so this will be our Fs, this will be our 2Fs. So now here around the Fs again the next sample will appear. Then around 2Fs our next sample will appear. Now you see this is 2Fm, this is 2Fm, that is this is 2 Hz, this is 2 Hz. This is also 2 Hz, this is also 2 Hz. Do you have any overlapping? No. So this area is no overlapping. Each sample we can clearly get it in the case. What is this case? Fs is greater than or equal to 2Fm. Because we have taken here Fm is how much? 2 Hz. And Fs is how much? 8 Hz. So it is a case of Fs greater than or equal to 2Fm. Now consider the case Fs. Now consider the case Fs is equal to 2Fm. So that means our second case. Fm is 2 Hz, Fs is 4 Hz. In that case also we are able to reconstruct the signal. So here when you take that, this is our F. So here now your Fs is how much? 4 Hz. So 0, at 4 your first Fs will come, then at 8 your 2 Fs will come, second, third sample, at 12 your 3 Fs will come. So 4, 8, 12 like that. Now at 4, around 4 your second frequency sample will appear, around 8 your third will appear. So now see, do you have any overlapping now? It is just touching, but there is no overlapping. You are not losing any information. So in this case also you can reconstruct your original signal very clearly. So this is the case Fs is equal to 2Fm. Now consider the last case. Fs less than or equal, not less than equal, only less than 2Fm. So here how much we have taken? Just see. Here Fm to Fs2 we have taken the equal condition. So if you have taken in this case Fs is equal to 2 Hz, then first will appear here, second sample should come here at Fs, third should come as 2Fs. So now see, around second my full sample should come like this. 4Fs, it should come like this. See, each of these places are overlapping. So all these places information will be losing. So this overlapping is called aliasing. So we can make sure that if you are sampling at a frequency Fs greater than or equal to 2Fm, greater than or equal to 2Fm case only we will be able to reconstruct the signal. So the first case not equal, it is only greater than. it's greater than 2 FM. Second case, Fs is equal to 2 FM. Third case, Fs is 2 Hz. So here Fs is less than 2 FM.